Okay, gravitation. I think you know the story behind gravitation, but you may not know the whole story. Just in line with what I was trying to say, nothing that has been ever invented or discovered has come easily. It has never come easy. Whatever we are enjoying has come through a lot of hard work. This again proves my point. You could call this man, Tycho Brahe, an astronomer of the 16th century, 15th century. He did not have many, sophisticated devices and all that, but using what he had, he would study the motion of the planets every single day. He would chart their course. He would say, I saw this planet today at this point, and then the next day I saw it at this point, and he studied them for 15 years. Did not come to any conclusions. But he had all the data that he collected, the charts that he collected, which he handed down to his student called Johannes Kepler. The student then worked with that data for another 10 years. Again, studying the motion of the planets, and at the end of it, he came to 3 laws that are called Keplers Laws, which we're going to study at the end of this chapter. But what's interesting is, everybody knows that all planets move around the sun in an elliptical orbit. That's Kepler's first law. Everybody knows that. But just to give that statement, doesn't it mean that he had to study every planet? Because if I'm going to say that every man is a fool, don't I have to study every person? Just think about it. Every planet. And some of these planets take years to complete an orbit. Are you with me? Can you understand? So they did a lot of hard work. If it takes 25 years to get 3 laws, that is what science is all about. Real hard work, and then you come to a result that changes generations. That is the subject. That's the nature of the subject. We'll come to that later. But now we come across to the 1676, I think, Isaac Newton, who has given the laws of motion. The story goes, he sat under an apple tree. Some of you would have heard it. The apple fell down, and if it was us, we would have opened our mouths and swallowed it, and would have never given a second thought about it. But this guy said, why did it come down? He said, is this the same force that keeps the moon going around the earth? Because Kepler's laws were already there. But Kepler did not know what force made the planets go around the sun. Are you with me? So Newton said, well, this could be a universal law. And there was born the universal law of gravitation. He wrote a book which has a big name, but the short form is Principia. In this book, Isaac Newton says that every object in the universe attracts every other object. So if somebody asks you, are you attracted to me? The answer is yes. And you can just stop and say, because of Newton's law of gravitation. Every object in the universe attracts every other object with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. I'm going to show it to you. It depends on 2 factors. It depends on their masses. It's 1687, my years. Okay. Principia is the name of the book. Isaac Newton is the man. And this is the law. The universal law of gravitation. Every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This is called the universal law of gravitation. So if you have 2 masses, m1 and m2, at a distance r from each other, then according to this law, the force between them depends on the product of the masses, isn't it? And inversely to the square of the distance between them. Now, this is a constant. Caps G is a constant called the universal gravitational constant. The number was determined by another scientist called Cavendish. He got this number. Just look at this number. You need to know that. Because it's a universal constant, you need to remember that. It is so small, isn't it? So even if the masses are huge, like on the face of the earth, I think the biggest masses that are movable or that are mobile are ships in the ocean, right? Don't we have huge ships? But even then, do you see two ships move towards each other on their own? The reason is G is very small. Are you able to get what I'm saying? So even if these products are so big, it's offset by the small number here. And also remember that gravitational force is always the force of attraction. And it is along the line joining the masses. It is along the line joining the masses. So in this case, M1 attracts M2, and M2 attracts M1. One is the action, the other is the reaction. Are they equal forces? Yes. So the moon attracts the earth, and the earth attracts the moon. Do they attract each other with an equal force? Yes. Because the force is determined by the product of the masses and the square of the distance between them, right? Another point is, what happens if you double the distance between two masses? You double the distance. The force becomes 1/4 of what it was before, isn't it? Do not forget the square term there. So that's what I'm talking about. So that is the universal law of gravitation. So that's the law of gravitation. Now let's talk about the gravity at the Earth's surface. So that's the Earth. And what you see right now is the radius of the Earth. Okay, on top, at the surface of the Earth, there is an object of mass m, a tiny object. me is the mass of the Earth, re is the radius of the Earth. Okay, what's the distance between the object and the Earth? Definitely re, isn't it? Because that size of that object is so small, there is no meaning in adding its, tiny radius to this. It doesn't make any difference. So according to the law of gravitation, and according to another law, the force between the Earth and the object. See, I've used two laws. This one is the law of gravitation, isn't it? What's this? That's Newton's second law of motion. Don't we know that the force that the Earth exerts on an object is called its weight? Come on. Mm-hmm. And the weight of an object is mg, right? Yes. So you have the same force represented in two different ways, using two different laws. One is the second law of motion. The other is the law of gravitation. Of course, the masses cancel out, and now we can find the acceleration due to gravity of any planet. Now, can't we find the acceleration due to gravity of any planet? Yes, knowing its mass and its radius, because this is a constant for all planets. Another thing is, have you ever wondered what the mass of the Earth is? We can find that out. Using this equation, if you rearrange, this is what you get. And because we know the radius, and somebody was asking me, how do you find the radius of the Earth? Do you have to dig a hole and you reach the center of the... How do you know when you reach the center? You just have to find the circumference, isn't it? And divide it by 2 pi. You get the radius, and that is going to be the equatorial radius, because you know that at the poles the Earth is slightly flat, isn't it? Okay, so knowing the radius and knowing g at the surface, and because we know the value of the gravitational constant, plug it in, you will get the mass of the Earth. Simple substitution will show you that the mass of the Earth is 5.98 times 10 to the 24 kilogram. Don't get me wrong, it's not 24 kilograms. It's 10 to the power 24 kilograms. Well, actually, we have determined the mass of the Sun. The mass of the Sun is 10 to the power 30 kilograms. That means the Sun is 1,000,000 times more massive than the Earth. We are talking about the universe now. So using the law of gravitation, we can pretty much find the masses of every planet. We have managed to find the masses of stars. We have calculated the masses of galaxies using Newton's law of gravitation. That's how powerful this is. We do not know whether we'll ever get to another galaxy, but we have managed to calculate their masses. That's what physics is all about. Okay. So that's the second part. The third thing is, surely the acceleration due to gravity decreases with altitude. Like if you were on the top of Mount Everest, which is like 8.9 kilometers above, what do you expect the acceleration due to gravity to be? Give me a number. Like on the surface, it's 9.80, right? So what do you expect it to be on top of Mount Everest? 7. Okay, how would you find that equation? How do you find G? Easy, because GME by RE plus H whole square. That's all, isn't it? All you have to do is add the height to the radius of the Earth. And when you do that, the result is amazing. What you get on top of Mount Everest is 9.77. So unexpected. It's less than 0.3% of a difference. So keep that in your mind, that as you go higher, of course, the acceleration due to gravity decreases, but not at the rate that we think. It decreases ever so slowly. Are you getting that? That's why I just had to show you that. Definitely decreases with altitude. And I hope that equation is well understood. It's simple. I just had to add height, so you get the new radius, and you plug it in, you will get it. You can go home and try to plug in the numbers, you will get it. The next question is, does the acceleration due to gravity change with depth? Like if you dig a hole in the earth and go down, what do you think is going to happen to the acceleration due to gravity? Is it going to increase or decrease? The crease is common for both words, so I could not really make out what you said. Because some people, I'm sure, said crease. You know, what do you mean, increase or decrease?
No, increase.
Increase. Increase. Yeah, what's the answer?
Well, I don't necessarily know.
See, in fact, as you go down, the acceleration due to gravity decreases. And at the center of the earth, it is 0. For the simple reason that as you go down, you have lesser mass below you that's attracting you. If you go to the center of the earth, what's the mass from the center attracting you? Nothing. So you have to take that into account. And I try to do something that's not in your textbook. So if you don't get it, just forget it. I try to prove it and get an equation. I am going to use the concept of density of the earth. What I'm trying to do is, look, I'm trying to find the mass that is below you. Because I know that it's only that mass that's going to attract you towards the center. Are you with me? So for that, I have defined density, and I tried to find the mass. Okay. So that's the earth, and I'm looking at a point that is d distance below the surface of the earth, as you can see. And there's only this mass here inside the sphere that's attracting you. So I'm going to find the mass of this part. For that, radius of the earth is RE. I know that part has a radius RE minus d, isn't it? That inner part is RE minus d. Density is mass by volume. And you know volume is 4 by 3 pi r cubed. The 3 goes to the top, and I get this. And so now the mass of this inner part, I need to find the volume of the inner sphere, correct? Which is 4 by 3 pi RE minus d whole cube times rho. Did anybody get what I did there? Because what's mass? Mass is volume times density, isn't it? Okay, what you see here is the volume of the inner sphere, and that's the density. You need to have tremendous concentration to understand. And so that's the mass. So now I can use the gravitational formula. And I'm going to, before that, substitute for density. You see, from the top, density is all this. So I've substituted, so I get rid of some of the terms. And I end up with RE minus D cubed times M by RE squared. Now I got the mass of the inner part, isn't it? Come on. In terms of the total mass of the earth. What you see here is the total mass of the earth. Are you getting what I'm saying? So, okay. Now I put it into the law of gravitation. And in place of this mass here, I'm going to put the mass that I got. Some cancellations. And finally, I end up with this formula. And I'm saying in this formula, if D is equal to RE, then you're right at the center, isn't it? If D is equal to the radius of the earth. Yeah. Look at this formula. If you put D is equal to RE, this term becomes 0. Therefore, if D is RE, G is 0. G at the center is 0. I thought it would be interesting to prove it, because otherwise some people may not believe me when I say. Because we walk with this misunderstanding that at the center of the earth, G must be a maximum. I've heard so many students have that idea. So I hope you got it. We would not have enjoyed our lives as much as we do today without satellites. But remember that the earth has a natural satellite of its own, which is the moon. Does anybody know with what velocity the moon is going around the earth? I don't expect you to, but maybe you know. It's about 1 kilometer per second, which is not very slow. 1 kilometer per second. And you know that the moon is real far away from the earth. Now the idea is, we looked at the moon and said if the moon can go around the earth, then we can have artificial satellites that we could make go around the earth, you see. And if you look at the picture of the present scenario, you would see thousands and thousands of satellites. It's scary. There are different types of satellites. But in all these satellites, remember, they are going around the earth, isn't it? Whenever an object goes around in a circle, there is a force acting on it. What's it called? I knew you would say that. The force, generally the force that acts on any object going around a circular path is called the centripetal force. And it's given by mv squared by r, isn't it? If it's an object at the end of a string, a stone at the end of a string, and you rotate it in a circle, then that centripetal force is the tension in the string. If it's a car going around a curve, then that centripetal force is provided by both friction and banking. Are you with me? But if it's a satellite going around the earth, then that centripetal force is provided by gravitation. So that's very important. So now we're going to say, generally the centripetal force is mv squared by r, correct? And that will be equal to gmm by r squared. Did anybody get what I said just now? We're going to equate it. You will see. R is the radius of this satellite. The mass of the satellite is m. The mass of the earth is me. What's r there? Radius of the, actually it's re plus h, isn't it? Re plus h. So understand that. Now this is what I told you just a moment back. On the right side you have centripetal force. But we know that in this case the centripetal force is provided by gravitation. So put them equal to each other, cancel the masses out, get an equation for the velocity, and then you look at it and say, okay, so you have g and me constants. R is the radius, which is a variable, isn't it? And it's in the denominator. Therefore, if the radius increases, the velocity decreases. And the moon is at such a great distance, that's why its orbital velocity is small. So what if you had a satellite very close to the surface of the earth? Could you find its velocity? Or could you find the velocity that you had to give it? Certainly. Don't we know the radius of the earth? If the satellite is really close to the surface of the earth, then this becomes the radius of the earth. And when you substitute the numbers, you get 7.9 kilometers per second, which is really fast. So if you want a satellite to go around the earth really close to the surface, then you got to give it this horizontal velocity. It's a real cool fact. Take a look at this. That's the Earth. I'm going to tie this to something else. If you are bored on a particular day and you decide to take a walk on the surface of the Earth, you think you are, let's say you're driving on the freeway, you think you're going horizontally, but you're not. Because actually as you go, you're also going down. Can you see that? Because the Earth's surface curves. And therefore, for every 7.9 kilometers that you walk horizontally, and this is not drawn to scale, okay? Every 7.9 kilometers that you walk horizontally, you go down by 4.9 meters. Now, why am I bringing that up? So if you take a satellite way up here and give it a velocity of 7.9 kilometers per second horizontally, we know that it's a freely falling object, isn't it? Vertically, how much is it going to fall through in every second? 4.9 meters. Delta x is v naught t plus 1 half at squared. Anybody with me? V naught, initial vertical velocity is 0. 1 half times 9.8 is 4.9 times 1 squared, 4.9. So, every second, this thing is going to go 7.9 forward and 4.9 down. Which means it's falling. A satellite is actually falling continuously. It's falling around the Earth. Are you getting it? And the reason why it does not fall onto the surface of the Earth is because it's curving exactly like the Earth is. So now you think, what if you only had given it 7 kilometers per second? Then you know at some time it's going to hit the surface of the Earth. So now you start thinking again, what if you give it something greater than 7.9? Now that's what you think. You think it'll shoot off? No. The orbit will become elliptical. Instead of being circular, it's going to become elliptical like that, right? You keep on increasing the velocity. When it reaches 11.2 kilometers per second, it'll escape from the surface of the Earth. That we will prove at the end of this chapter. This is called the escape velocity from the Earth. So if you can throw anything, that's why I said, if you could throw your husband or your wife at that velocity, you can get rid of the person. But that's too big a velocity, and I'm so glad about it. Because if this was like a small one, we would have had murders upon murders here. People just vanishing into space. I hate him. I threw him up. He's gone. Sounds like a cartoon, but I hope you understood this. Did you? That is about. But now, can you find out an equation for time period? What do you mean by period? Time taken to go around the Earth once. Okay, yeah. How do you find out a formula for period? Let's be thinking as you're listening to me. How do you find time? What's the basic relation between time, displacement, and velocity?
Distance by all of that.
All right, distance divided by time gives you speed. Let me talk about speed because it's changing direction, okay? When it makes one circle, what's the distance? What is the distance?
It's the radius of or the circumference.
Circumference, which is 2 pi times the radius. Isn't it? Okay, there you go. So to find the time, you take the distance, which is the circumference, and divide it by the velocity or the speed. Distance divided by, correct? And then substitute for the speed, which we have there. We have the formula for speed already, so I'm going to substitute for that. And I get this, square root GME by R. But that looks ugly, because there's a square root there, so I'm going to square both sides. When you square both sides, what's going to happen? You get rid of the square root, but this becomes an r squared, isn't it? And so this r goes back to the top and it becomes a r cube. That is what's going to happen. So t squared is 4 pi squared gm r cube. Giving us Kepler's third law. Actually, this is Kepler's third law, but I'm talking about a satellite going around the Earth, isn't it? This is true for any planet going around the sun. This is Kepler's third law, that the square of the time period of revolution is proportional to the cube of the average distance between the planet and the sun. Now, why did I have to say average distance? Why did I have to say average distance? Because it's elliptical. And you know an ellipse has a major axis and a minor axis. Haven't you studied conic sections in math? So when you take the average distance, you're going to say major axis plus minor axis divided by 2. That's why I have to say that. So that is Kepler's third law. The square of the period of revolution of any planet is in proportion to the cube of the average distance between the planet and the sun. And it's so perfect. If you take this ratio, like if you take t squared by r cubed for all planets, then it's given in your textbook. Wouldn't you get a constant? Hold on. Wouldn't you get a constant? T squared by r cubed is a constant for all planets. And it happened by chance. That's the part that beats me. Such an order in the universe. Even if you take the whole universe, it's like there is perfect order. And to say that this came out of a big blast is nothing beyond being absolutely foolish. Because a blast creates chaos, not perfect order. Wait until I teach you thermodynamics and we talk about entropy. Science cannot answer this question. What is a geosynchronous satellite? I'm sure you've heard about it.
It stays in the same position above the Earth.
Yes, so the Earth is rotating. Be with me, the Earth is rotating, and believe me, it is. And it makes one rotation in 24 hours. Everybody knows that, right? I'm talking about the spinning on its own axis, not going around the sun. For that, it takes 365 days about. So, it takes 24 hours to spin on its own axis, the Earth. And when we send a satellite, don't we want that satellite to stay on top of us all the time? Especially if it's used for communication purposes. Do you want that satellite to be roaming around, go on top of Afghanistan? Well, if it's a spy satellite, yes. But if it's a communication satellite, we want it to be on top of where we launched it, on top of our country, so we can use it, right? So then, doesn't the satellite have to be spinning with the same angular speed as the Earth? Okay, what is angular speed? Did we talk about angular speed before? We did. All right. Angular speed, omega, is theta by t. Did I tell you about this?
No.
If not, here it is. Angular speed is theta over t. Just like velocity is x by t. You see the comparison? You see the comparison? You're talking about an object that is rotating. So we're talking about an angle that it makes. It goes from A to B in a certain time, t seconds, right? And during that time, the angle is theta. Now this is omega. It's called the angular speed. What's its unit? What's this unit of angular speed? What's the unit of angle?
Degrees.
Nope. Radians per second. So whenever you see this, you have got to write rad per second, radians per second. And there is, of course, a relation between these two. That's simple intelligence, because if it's going fast, then you know that its angular speed is also greater, isn't it? And this is the relation between the two. If you like it as a product, some do. Then your speed is the product of angular speed and the radius, which you can find easily. Do you want me to derive it in a minute? If you help me. You help me by defining angle. I'm talking to math scholars. Define angle. I expected this. Because it's the basics. See, angle is the length of the arc divided by the radius. That's the definition for angle. Arc length divided by radius. That's how angle is defined in radians. Okay, I'll prove it to you. When you go around the circle once, you get the circumference, isn't it? How much is that? 2 pi times r. Divide by r. What do you get? 2 pi radians, which is 360 degrees. Now that should make sense. That's why we say that the angle around a point is 2 pi radians. That's the reason. 360 degrees. So keep that in mind. Why did I bring that in here? That means theta here is AB by R, right? Correct? Theta here is AB divided by radius. Okay? Divide both sides by T and you have your formula. Divide both sides by T. What's theta by T? What's theta by T? Omega. And you see AB by T here? What's that? What's AB by T? Linear speed. Displacement by time. So I got my formula. Here it is. Omega is V divided by R. That's how you get the relation between the two. Now I had to say all this because I was talking about a synchronous satellite. Please don't forget that. I want you to find the height of a synchronous satellite and send it to me. I said this to the other class. One student sent it to me. And I gave him a ton of credit. Because if it's only one who does it, he gets a lot. Because I get tremendously happy with him. If it's like 20, you get a little. It's shared. So be careful when I find the height of a geosynchronous satellite and send it to me. I'll give you how to find it out. Here it is. Do you know the time period of a geosynchronous satellite? Yes. How many hours? 24 hours. Can you work out a problem in physics in hours? No, you can't. You have to change it into seconds. So I gave you the time period. Don't you know these two? What's this? That's the mass of the Earth. We're talking about a satellite going around the Earth. We know this. We know this. Can't you find out the radius? And then you know what to do to get the height. Simple. And the height is going to be really big. Our communication satellites are not close to the Earth. They are really high above. Find that height. Remember, we're talking about real things. That's how we are able to watch the Winter Olympics in Sochi, right? Using satellites. That's how you are able to use your cell phones wherever you are. This is the reason, because of communication satellite. You get it. Show the calculations and prove that it's 36,000. It's 36,000 kilometers above the Earth's surface. That's not close. I want you to realize that. Prove it, get it. Might be a question in the exam. You never know. Keplers laws, finally. Keplers laws of motion. Number one. Yeah, number one, I told you Kepler's first law. Any planet moves around the sun in an elliptical orbit, isn't it? Watch this. Isn't this an ellipse? Yes. And watch carefully. That's the planet. That's the sun. This is the point where it's farthest away, isn't it? And that's going to be the slowest motion. It's going to move really slowly when it's far away. And isn't this the point when it's closest? It's going to move fastest there. The points are called aphelion and perihelion. Okay? And then at other points, it's going to have velocities between the two. But what's important is the path of each planet is an ellipse. And did you know that an ellipse has two foci? That's the plural of focus. Okay? And this is one of the foci. If you watch carefully, you see the second one. Do you see it? Yeah. So as the planet goes around the sun will be at one of the focuses of the ellipse. That is Kepler's first law. Here again, I've told you that it's slow here, fast here. We're going to prove that when we study angular momentum. Another chapter, we're going to prove why it's slow here and fast here. Okay. That's coming. But the second law,
What's the distance?
the second law is a little bit harder to understand, so you have to pay a little bit more attention. Watch this. Let's consider that the planet goes from A to B. Didn't I tell you that it moves fastest here? I did. And then after some time, it moves from C to D. Right? That makes sense because it's moving slowly there. But if you take this area, you see, if you take the shaded area, they'll both be equal. But I'm talking about the same time that it took. In a particular time, it went from C to D, and in the same time, it went from A to B. Although the velocities are different, if you take the areas, they're going to be, that's Kepler's second law. So an imaginary line drawn from the planet to the sun, that's the imaginary line drawn from the planet to the sun, sweeps out equal areas in equal intervals of time. That's Kepler's second law. So what's really important is equal areas in equal intervals of time. We can call that the areal velocity being constant. Areal velocity being constant. So that is Kepler's second law. Once again, in that diagram, you see this is one focus, but the next one is here, right? Okay. And we talked about Kepler's third law already. We did. I hope you remember when I was talking about the satellite. And if you watch very carefully in this picture, I hope you're able to make it. Isn't this t squared? It says the square of the orbital speed. And what is this? Cube of the semi-major axis, which is the average distance, okay? Do you see that you get a straight line for all the planets? Which means that it's a constant, isn't it? When you divide, it's a constant. Perfect. It's not an approximation. And they are running up to 10,000 years. Look at that. More than 10,000 years, but still there is perfect order. So this is Kepler's third law. The square of the time period of revolution is proportional to the cube of the mean distance between the sun and the planet. That is Kepler's third law. Mathematically, t squared is proportional to r cube, which we did prove for a satellite, is also true for a planet. Thank you so much, and if you like this video, share it, comment on it, and study it.